Hello, pre-calculus friends. Happy Monday morning. Today, don't know what's going on with my photo booth and the calculator that I've got on the computer. Everything just actually froze up and started getting all wonky on me. So I'm gonna have to switch back and forth with Desmos, making this thing work. But we're gonna get it going. So it is beginning of May. Hope you enjoyed your weekend. I got outside a little bit for you today. Now, the next week, 2 weeks, what we're going to be looking at a little bit of some applications of exponential logarithmic functions. The logarithms are going to come into play when we're really solving equations and dealing with exponential functions, as we saw with the properties where you can use the logarithm to pull the exponent out of the exponent, turn it into multiplication. Now, today, we're going to start looking at something, and I am going to aim to make you sad. That's my whole mission as a math teacher, make you sad. Yeah, it's no surprise to me either. But then, I'm going to fix it a little bit. I'm going to make it a little bit less dreary, less kind of like doom and gloom. So, I'm going to pull us in. Everybody's favorite physicist, probably one of the only physicists we can name. I'm going to pull up an Albert Einstein quotation. Albert Einstein once said, "Compound interest, the most powerful force in the universe. Compound interest is the eighth wonder of the world. Whoever understands it earns it. Whoever doesn't pays it." And the idea behind this is that if you understand compound interest, you can put your money to work for you, and you can make money off of your money. And if you don't understand it, if you don't understand how to invest and to put money into the bank and save it long term, then you're going to be the one ending up paying compound interest rates on your credit card. You're going to pay an exorbitant mortgage. You're going to pay car payments. You're going to wonder where all your money is. So we're going to talk about that over the next few days, weeks or so, and go. We've got Einstein. We know our compound interest formula, our A, our final amount, our P, our principal, 1 plus R over N raised to the NT exponent. And the idea is if you put money in, you can save it long term, blah, blah, blah. It builds. Banks pay you interest. You receive dividends on your investments, and you have more money later on. So let's talk about this. I've been thinking in this time of remote teaching, making it work a little bit. I very much enjoy my job. But one of the things I enjoy my job is seeing you. Yeah, you, the one who's actually listening to my video right now. The one who actually puts up with all my stuff. The one who likes the video down below. Come on. You're the reason why I keep doing this. But I recognize also someday I'm probably going to want to retire and move on from this. Maybe I'll consult. Maybe I'll just do pre-calc and not all the other stuff that I don't like to do. Maybe I'll just, whatever it is. Someday you'll be there as well. We're 18, 17, 18, 20 years, whatever we are. There will come a day where you're tired, where it'd be nice to have a choice to move on. So, let's say when we're 65, 45 years from now, I'm going to round up your age a little bit to 20 years old. Let's say we need $1 million, $1 million in the bank. By the time we're 65 years old, we can retire, take it easy. That's 45 years away. Well, if we want to do that, and we say we've got compound interest, monthly return rate 5%, how long, or excuse me, not how long, we know 45 years, how much money do we need in order to hopefully retire someday? Well, we're going to put all of this information into our compound interest. We know A is our $1 million. It's the final amount that we have. R is going to be our 5%. We are doing this compounding monthly, so N is going to be 12. N is again going to be 12, and time is 45 years. So we substitute everything in. Well, we can very easily solve this. Over on the left side, we've got 1 million equals P times all this. I'm going to go over to Desmos. There we go. We're going to end up dividing 1, 2, 3, 4, 5, 6 divided by 1 plus 0.05 over 12. Our exponent 12 times, nope. So I did this all on the calculator earlier, and it was easier that way. We need, over here on the right, $105,893. Switch back over. Oh, come on. Oh, got the math typed in there already. we need $105,000, almost $106,000 right now. So that's at age 20. If you hope to retire someday, $1 million when you're 65 years old, you need $106,000 right now. So, who's got it? Can you ever retire then? Is that ever going to be possible? Why even bother? Well, you're going to hope you enjoy school, hope you enjoy this, because you're going to be working for a long time. Well, let's think instead. What if instead of needing $106,000 right now, what if we instead just say, we're a professional, we've got a career, what if we take $250 out of each paycheck over the course of our career? We don't even miss it. So if we can set a little bit of money aside, what happens then? Well, I'm going to take $250 out of the paycheck that I'm getting this Friday, and I'm going to let that sit in the account for the next 45 years. Now I'm going to assume that I get paid bi-weekly, so I'm going to see some numbers here. I'm going to do my compound interest. I've got $250, 5%. I'm doing this compounding 26 times because I'm going to do this every paycheck, and I'm going to assume bi-weekly paycheck, so 26 times a year. So my money, I can take $250 out of this week's paycheck. Now, I recognize that right now we are working working at Stop and Shop or whatever you're doing, Highland Market. It's a little bit hard to save $250, but hopefully, you've put that college education to good use and you can save some money. If we've got $250 and I let that sit for 45 years, that actually turns into $2,366. So that's the amount of money that I'm going to get from just this Friday, this paycheck that I'm getting this week. Now, next Friday, or the Friday in a fortnight, 2 weeks later, we're going to do this again. I'm going to take $250 out of my next paycheck. But what's going to happen is it's going to be in there one less pay cycle. So rather than being in there for a full 45 years from now, it's going to be in there for 45 years less one pay cycle. So that second amount, next paycheck's $250. It's going to be in there, compound interest. I've got subtract 1 up here because it's in there for one less period. So over the next month, if I take $250 out of this paycheck, $250 out of the next paycheck, that's $500 that I just kind of invest. $500 is going to turn into $4,700. Ooh, $500 now, $4,700 later. That's not too bad. Let's do it again. The next paycheck. Now, it's going to be in there for 45 years, less 2 different pay cycles. So now what's happening is, how many times are we going to have to do this? So, oops, that should be a subtract 2 there. The number's correct. So $250 this week, $250 next paycheck, $250 the paycheck after that. All of a sudden, we're up to $7,500. That's pretty good. We're going to keep doing this every pay period for 45 years. If we get paid bi-weekly, we're going to do this. Now, this is the money that we have. Oh, those should all say $250. Those should all say $250. We're just going to take it as is. So you notice we've got 26 paychecks. We're going to do this for 45 years. Next paycheck, 26 paychecks, 45 years, minus 1 because it's in one less cycle. Minus 2 because it's in one less cycle. The meaning behind this, we've got that subtract because it's in there for a less amount of time. That ... that I have in there means everything in between. So we're going to do it every single pay period all the way up until the last week right before retirement. That's actually 1,170 different pieces that we need to add together. And I got that by doing 26 pay cycles for 45 years. You get that many total paychecks. So if we want to figure out $250 every paycheck for 45 years, we'd have to take this, plus this, plus this, plus this, 1,170 times. I'm going to pause for a little bit. Start calculating. Keep going. You got to type it all into the calculator. Every single, if only there's some easier way to do this. let's go back to our polynomials. I'm going to go on. From past experience, adding together a polynomial, we can actually shorten this using what's known as the sum of a geometric series. Geometric series when we have the exponent is changing over time. This goes all the way back to Algebra 1 when you had a geometric sequence. So we've got this identity, this equation, that if we want to add together a string of terms where we have the exponents are decreasing all the way down to 1, we can actually shorten it up as this statement. Now for us, this value a here, this base a, is actually our exponential base, this 1 plus r over n. That's coming back from our compound interest statement. Now the exponent here, k minus 1, k minus 2, a k is the nt. That's the exponent that we have from our compound interest. So combining this, we can shorten this. All of this added together, those 1,170 different pieces that we need to add, can be combined into one statement. Multiplying by how much we're saving, our principal each time. I'm going to call it my deposit amount. We have what's known as the systematic savings formula. The systematic savings formula is a way of repeatedly depositing money and seeing how much total value we have after the end of some period of time. Compound interest takes a single deposit, a single payment, and gives you an amount after so many years. This is what we're calling our systematic savings formula. Takes an initial amount, and we're going to repeatedly deposit the D value. We've got our interest rate, R, shows up 2 different locations, divided by N. N shows up 3 different locations. So it's deposit amount multiplied by 1 plus R over N to the NT minus 1, all of that in my numerator, divided by R over N. So we've got our future value, we've got the amount from each deposit, we've got our annual interest rate, the number of deposits per year, and the time in years. New formula, write this down. All right, so let's try this out. Back to what we had. We were going to do $250 per paycheck in an account earning 5% interest, 5% compound interest. How much is that going to get us 45 years from now? Now the whole point of this, going back to the start, we want to retire with $1 million. In order to retire with $1 million 45 years from now, we need $106,000 today, or at age 20. Not likely that you're going to have that. Nothing, no personal judgments, but let's at least save a little bit. $250 a paycheck, let's see what happens. So I've got my formula. In solving a problem, identify the formula that you're going to use. I'm going to identify the information that we have. Now we are going to find our future value. And I get that. How much will be in the account? That's asking what's our future value. We're going to make regular deposits of $250. We have compound interest, 5% interest. And we're going to make 26 deposits per year. And we're going to do this for 45 years. So solving, evaluating, I'm going to take my information, I'm going to substitute it into the equation. Now what I see is everything here is on the right side of the equation. I can put everything into the calculator all together. I'm going to go back over to my Desmos, evaluate that. So we've got 250. Oh, that should be 26, not 12. We're doing 26 paychecks per year. So we've got the future value, the deposits, 1 plus R over N raised to the NT minus 1 all over R over N. Ooh, look at that. $250. Now, $250 right now might seem like a lot, but hopefully you get to a point like in a career where $250 a paycheck, you might not even notice that's gone. Now, we've heard of different things like an IRA or a 401k. Someday you might have a company, you might work for an employer that offers a 401k, or in my case as a public school employee, I'm offered a 403B. If I opt to put $250 from my paycheck into an account, I don't pay taxes on that right now. I can pay taxes 40 years from now when I retire, but I don't pay taxes right now, and as a result, I'm actually taxed at a lower rate, meaning I'm saving a lot more money. But $250, look at this, 1100, there's $1,100,743. So I'm going back to Word. $250 a paycheck gets us $1.1 million later on. Now that's a long time, but the point that I want you to see is a little bit each paycheck adds up quite substantially. Now follow throughs on this. How much are we actually depositing? Excuse me. So the total deposits, how much money are we putting in? We're saving $250 n times a year for T many years. So our total deposits, 250 times 26 times 45. Over the course of our career, we are putting aside $292,500. That gives us $1.1 million later on. Another follow-up question, how much interest is earned? Well, the interest earned is the future value, $1.1 million, subtract our total deposits that we just found. So what we see is by saving $250 each paycheck, we end up with $1.1 million. We have earned $808,000 in interest. That's quite a nice little chunk of change for doing nothing, for just saving some money. And you end up saving yourself some tax if you put some stuff aside each time. Let's take another example. This time now, 45 years, retirement, that's something to think about. What if you need to save up for a house? You want to save for college education. You want to save for car. This is the formula that works long-term for you. This is your retirement. This is your long-term savings formula. All right. What will be the what will be the future value of an account 10 years if $400 per month is deposited into an account earning 3% compounded interest? All right, we've got our formula. We've got what we're trying to find. It's stating what will be the future value. We're going to look for F. Looking for a deposit amount is $400 each month. We've got 3% interest. We're doing this monthly because it states that, and we're doing this for 10 years. It's a matter of substitute everything into the equation. I can put all of this into the calculator at one point because it is all on one side of the equation. And we can find our future value. $400 a month for 10 years turns into $55,000. If you save a little bit along the way, it adds up substantially. Now, as we go through, we've solved for F. We can also solve for D, and we can solve for T. Got one more example right now. We're going to solve for D. Tomorrow, we're going to go through solve for T. All right. We've got a student, a kindergarten student. Parents wish to save $200,000 to pay for the estimated costs of their college education. We're going to save in a fund that pays about 8% interest compounded quarterly. So long-term stock market average now, the last 2 months has been pretty bad, pretty good, depending on where you're at. But long-term stock market average over the past 100 years is about 7%. So these are reasonable numbers. Here's the question. How much should the parents deposit? Okay, we're trying to find the deposit. At the end of each quarter, okay, we've got 8% interest. We want $200,000 in 13 years. So we've got our formula. We identify what we know, what we don't know. We want $200,000. We don't know the deposit. We know we have 8% interest. We are compounded quarterly, and we're going to need this in 13 years. So substitute everything into the equation. Now I notice we're trying to solve for D, the deposit value. That's multiplied by this whole chunk. So what I'm going to do to solve is, since we are dividing by 0.08 over 4, I'm going to multiply. Since we are multiplying by the portion in the numerator, I will divide by that value. So rearranging the equation, it's d multiplied by all of this. We can divide by or multiply by the reciprocal. That will isolate d. This allows me, everything's on one side of the equation. I can just plug it into the calculator. We've got 200,000. So we have that's the wrong thing. 0.08 over 4. We get 222182. So we would need to save $2,221.82 each quarter. Or, what's that, $700 a month. So, those are real numbers. How much is your school paying? We're going to take a look at that coming up soon. So the whole thing that we've got here today is we have what we call the systematic savings formula. This is when we have repeat deposits. We can find the future value after so many years. We've got D is the deposit, the regular amount that we are continually putting in at regular periods of time. R is our interest rate as a decimal. N is the number of deposits per year. And T is, of course, time in years. So try it out. Let me know if we've got any questions. Good luck.